Good evening. My name is Michael Roberto, and this is my lab partner, Guthrie Hayden. And this is our presentation for Lab 9, Heat Treatment, Hardness, and Phase Transformations. So for the introduction, for context, we will be exploring the effects of heat treatment on the hardness of steel. And our objectives will be to perform heat treatment on different metals and see how that affects our Rockwell B and C readings. We'll also understand the Rockwell and Burnell hardness tests, investigate the correlation between processing and hardness, anticipate changes in Rockwell B and C hardness due to the heat treatment. And this leads to our hypothesis, which that the oil quenching will result in the most hardening, with annealing being second and water quenching being last. So for our methodology, we have our experimental setup. And during this experiment, we had a Rockwell hardness tester, steel 1018 and 1045, brass, aluminum, oven, and a Burnell hardness tester. And then you can see in figure 1 is the oven that we use to heat up the steel 1018. Figure 2 is a Rockwell hardness tester. Figure 3 is the specimens, and the circular specimen on the bottom is the specimen we used to make sure that the machine was running right, as it has known Rockwell hardness values, and we use that to test the machine and make sure that all the values were correct. And from left to right on the top of figure 3, we have the specimens aluminum, brass, 1018 steel, and 1045 steel. And figure 4 is the Burnell hardness tester. So for the procedure of the Rockwell hardness testing, we recorded the specimens, composition, and pre-treatment Rockwell hardness, and we did this for all the specimens, so the aluminum, brass, steel 1018, and steel 1045. The steel 1018 was placed in the oven, and it was heated to roughly 840 degrees Celsius, which gave it a bright red color. And then we quenched the steel 1018 in oil or water. And then after it was cooled down, we cleaned the surface and we tested its hardness using the Rockwell B and C testing. And then we repeated the steps of quenching the specimen. If we didn't do it before in oil, we did it in water and vice versa. And for the procedure for the Burnell testing, this part was mostly done by the TA, and we gave the TA our aluminum specimen, and he tested it using the Burnell testing machine. And from that, we were able to find the values that will be shown in the data section.
Awesome. So in part of our data collection, we had 3 different trials, and that averaged into, this final value that we used among the aluminum, the brass, the 1018, the 1045 steel, both when it was annealed and treated with various oil and then water. And this is important because the surface of the material that we're testing is not completely, homogeneous. It's not completely flat, because in the labs before, or maybe just small microscopic issues, it's not completely flat. So we actually took 3 different tests to have an exact value, so then we could, measure our sort of expected values for the Rockwell test, just in terms of accuracy. As you see that in the right side of our column, of each column, we have the weight and then the indenter. This is just to further explain the difference between the Rockwell B and C hardness tests. So Rockwell B has slightly less weight, only 980, compared to a 1471 weight for Rockwell C. And then the indenter is slightly different as well. So we have the ball on Rockwell B and then the diamond on Rockwell C. So this is just to establish a little bit more of a variance in terms of how we can test our different substances, right? So for example, with the 1018 steel, we tested it using both B and C. So this is important because we can get an average value for those. Speaking of which, you can see on the right side, the very top, we have our average Rockwell B and C hardness tests for all the various types and treatments of 1018 steel. So this is super important because the Rockwell B and C values for different treatments show the impact. They show the actual impact of the heat treatment on the hardness level. And then this really helps to mitigate sort of this impact of potential outliers, as I mentioned in the beginning. And basically all of this is supposed to maximize the set value that we need for these tests.
A result and analysis. On the left side, we have the bar graph, which shows the 1018 steel versus the Rockness C hardness. And as you can see from this, the annealed created the second most hardening, with water quenching being last and oil quenching being the most. And this correlation can also be seen in the bar graph to the right, which is the 1018 steel versus the Rockwell B hardness testing. And the values got lower for the annealing and the water quenching as compared to the untreated. However, the annealing did create more hardness than the water quenched, which is the same case for the Rockwell C, and the oil quenching created a greater hardness than the untreated, annealed, and water quenched, which also correlates back to the 1018 steel Rockwell C hardness in the graph on the left.
So this is super important because the Brinell test that we actually use the equation that the TAs give us, which relates the diameter of the impact crater and the overall tensile properties of the material that you're pressing into. And so the Brinell test is very interesting because it gives us an array of different values. But mainly for our results for the Brinell, we got pulled aside by the TA and he did the test for us. And then we got data from that. But the average HRB was 84.33. The depth penetration, which was on the previous slide, but if you did not catch it, it was 0.82 millimeters. The overall tensile strength is 290.95 megapascals. This is super promising because the literature value ranges from 58 to 550. So we're actually right in that center area, right where we should be, perfectly sort of in the average in between. So that's very encouraging in terms of the accuracy of our data. So overall, the Brinell test is very accurate in terms of how specific you can get the depth relating to the HRB. And then this really highlights the difference between the Rockwell and Brinell testing, as I mentioned beforehand. There is a clear difference between the cooling methods based on the bar charts, because the water quenching was kind of fluctuating a little bit between B and C, but the oil actually was very steady in terms of the not the accuracy, but the strength that it gave the material. So that was very interesting. Then the aluminum tensile strength accuracy again was very important in determining the accuracy of the Brinell test. And then of course this has a lot of real world applications because we need things to be very accurate in its own strength, whether that be to build bridges or buildings or anything that has a load bearing on it and is reacting with different shear forces or tensile forces. So this was really a good sort of combination of a lot of our previous labs because we sort of can understand the various tensile properties relating to the forces, especially a sort of a strong downward force that we tested in the lab. And so overall, our hypothesis was supported. Oil quenching creates the most hardening, with annealing being second and water quenching being third. This completely supports our hypothesis. And as I mentioned, there are broader implications because we realize that when we quench something, we are altering, the alignment of the chemistry. This can make it either harder or softer in terms of the Rockwell readings in Brinell. And so again, this is super important because we can optimize certain material properties and use it to our advantage, and in terms of a production standpoint, having products that we can cheaply anneal or quench can be super great in terms of minimizing the weight or the cost and manufacturing more of them. So overall, this really has like a lot of broad implications that maybe we don't see straightforward.
For the future work recommendations, we could use different materials and for this, and we would have been able to find how things change with those different materials based on the cooling methods and how those material properties and like alignments of the materials change. We could also just use different materials of the 1018 steel and the brass and the 1045 steel and the aluminum as some of them all weren't in the best condition. We could also use different cooling methods in order to see how those change the hardness of the materials. Instead of using oil for quenching or water for quenching, we could have used a different type of liquid and seen how that related and was different from the oil and water and annealing. And also we could use a lubricant to minimize friction, as when you are using the Rockwell B and C hardness testing method, especially Rockwell C, when you use the pointed diamond tip and it cuts into the materials, there is friction between the diamond tip and the material, which can cause friction, which can change up the data a little bit and skew the data as well. And yeah, and these are our references. Thank you very much and have a
Thank you
well.
so much.